Okay, time to begin. The people I don't see are Chad, Bridget. Chad says he's here. Bridget, Sally, and Jerry. See who this is. Bridget. Okay. The material starting today will not be on the exam next Tuesday, right? You want to make sure you have time to review stuff and not just have it fresh at the exam. So we're starting talking about relativity. So let's get into it. Yes?
So you said that whatever's starting to be covered from today onward won't be on the exam?
It will not be on the exam this next Tuesday. That's correct. Okay, reference frames are a really big deal in relativity. In fact, relativity is the discussion of how measurements in one reference frame relate to measurements in another reference frame. So we have to start any discussion on relativity by being clear about our reference frames. So starting off, your reference frame needs to have an origin, right? A point of reference in that reference frame. And so we usually represent this point of origin with coordinate system, X, Y, Z coordinate system, and the origin is our point of origin. And then we make measurements in those reference systems, or reference frames. So I have an example here. I have two people walking hand in hand on a sidewalk. And so they're walking at 1.3 meters per second with respect to the moving sidewalk. So, they're in the airport. Got the long moving sidewalk. They're walking along at 1.3 meters per second for their speed compared to the sidewalk. But that sidewalk itself is moving at 2.4 meters per second. Right, so if they were just standing there, they'd be going 2.4 meters per second compared to the building. If the person is walking and they're just looking down at the ground, they would simply say, I'm walking 1.3 meters per second. Because that's how fast they're walking with respect to the reference frame of the moving sidewalk. But if the person instead were to look out to the side and see all the shops going by, how fast would the person say that he or she was traveling? They would add the two together and say 3.7 meters per second. And both of those are correct answers. It's just with respect to a different reference frame. And a very fundamental thing about relativity is that the two reference frames are equally valid. You don't say, oh, no, you're incorrect. That 1.3 was wrong. Only the 3.7 was right. It doesn't matter which reference frame you measure with respect to. As long as you make the correct measurement, it should be correct. It should be valid. So relativity is dealing with how to compare these. Now, we'll learn real quickly about Galilean relativity. Galilean relativity is pretty simple. Inertial reference frames is an absolutely vital part of relativity. Everything that we will be doing, all the calculations that we'll be doing today, tomorrow, well, not tomorrow, I guess, Friday, probably next Monday, they're all going to be in inertial reference frames. So we need to know what an inertial reference frame is so we can determine things about the reference system we're using. So an inertial reference frame is called an inertial reference frame because it's a reference frame where Newton's first law is valid. That's what it means to be an inertial reference frame. What is Newton's first law? It's known as the law of inertia. And it says that an object in motion stays in constant motion unless an external force acts on it. Up to this point, we've always said, yes, that's a fact, Jack. But now we're saying only inertial reference frames have that as a fact. And we have seen some examples of non-inertial reference frames. Example of a non-inertial reference frame is a reference frame that is itself accelerating. So if you are on a merry-go-round, you tend to think, I'm sitting here on my little seat. I'm not going anywhere. I'm staying right on this seat. But you also know that you are accelerating, right? You know that you're staying stationary, but you have to kind of push in toward the center, or you're going to slide off. So that reference frame of on the merry-go-round is not inertial. Or as we like to say, it's a non-inertial reference frame. Because in that reference frame, if you don't apply that force toward the center, you're going to go flying off. So there would be an acceleration without a force. Now, if you want to be technical, and I think I have it on the top of the next slide, so let me go there instead of doing it all on its own. Nope, I have an example. I'm going to come back here, say that if I want to be technical, then talk about that merry-go-round again. If you want to be technical, when you're standing on the surface of the Earth, you are accelerating. Because what's the Earth doing? It's rotating around in a circle. So we are accelerating. Hence, technically, the surface of the Earth is a non-inertial reference frame. But the acceleration is small enough that we will treat it as an inertial reference frame. And of course, then one would say, well, what if we just talk about the center of the Earth? Well, the Earth is orbiting around the sun, so we're still accelerating just the Earth itself. And, well, what if we talk about the sun? Well, the sun is orbiting the center of the Milky Way galaxy. Well, what if we talk about the Milky Way galaxy? The Milky Way galaxy is interacting with the Andromeda galaxy and the large and small Magellan clouds, as well as the Sagittarius dwarf galaxy that's currently inside of us. Yeah, we're currently ripping apart the Sagittarius dwarf galaxy. That's what's going on in the Milky Way galaxy times. So to get to an absolute inertial reference frame is virtually impossible. So we take approximations. This is approximately inertial reference frame, and we run with it. So now coming back to the picture here of a merry-go-round to illustrate, does anybody remember what this was called when we talked about it the first time? It's an effect. It starts with C. The Coriolis effect. If you are on a merry-go-round and you're spinning around in a circle and you throw the ball straight across the center, in your reference frame, that ball does not appear to go straight. It appears to curve. But if you were in the tree's reference frame, it would see the ball go straight. That illustrates a difference in the reference frames, right? The non-inertial reference frame, it curved, which would have required a force to curve, right? So it's non-inertial because it doesn't stay in constant motion in a straight path, even with no force acting on it. So that's a nice, clear example. I think I told you guys before, we had a little demonstrator when I was in grad school. It was a teeter-totter that could rotate. And so we had it set up in the lab room, and I, the lab instructor, and my students got a little too rambunctious. And I, the bad one, came across, and I leaned forward so my back didn't hit the desk, but the teeter-totter did and just completely took that leg out. Bad times. But it was a good demonstration for this effect because we had a ball. We're going around as fast as we can, trying to throw the ball at each other. It's a lot of fun. I mean, that's what physics is, right? You probably by now have equated fun with physics. First clicker question, which is open for answers now. This is a multiple answer, so put in all the ones that you believe are correct and then hit enter. Which of the following is an inertial reference frame? To a good approximation. Oh, Jerry never came, right? I'm sitting here waiting for Jerry, and he's not here. Okay. The answers that we got. So there's some clear confusion. So let's remember what makes a reference frame inertial. Okay, if the reference frame is not accelerating, then it's an inertial reference frame.
How is the inertial frame on the merry-go-round? How is that inertial if it was accelerating?
It was not. It was non-inertial.
Oh, okay.
Okay, so talk with your friends about each one of these and discuss whether it's accelerating or not, and thus if it's inertial or not. Yours ready?
Oh, yeah.
Okay, it's now open for repolling. Let's see if you move toward correct or move toward error. I pray toward correct, of course. Okay, starkly different results. And that's good. We moved toward correct. 15 people were correct for the first two answers. One person for the next one, 4 for the last one were incorrect. The correct answers were these two. Because the stationary car has an acceleration of 0. A car with constant velocity, by definition, acceleration is the rate at which velocity is changing. So if the velocity is constant, that's an acceleration of 0. Car accelerating along a straight road. Ooh, that had the word acceleration in it. Good tip-off that it's accelerating, and thus it's not an inertial reference frame. And the final one, a car moving around a curve at constant speed. That would be just the same as being on the merry-go-round. If you're in the car going around the corner at constant speed, you need a net force toward the center to keep you in the car going around. So if you're sitting in that car, to stay going a circle, that is to stay in your opinion, to stay stationary, you need a force that's pushing toward the center of the car. So that makes it non-inertial. So this identification of inertial versus non-inertial reference frames becomes important. Things like, you might have heard of the twin paradox. The way we solve the paradox is to realize that one twin is in an inertial reference frame and one is not. And, well, we haven't talked about it yet, so. But that's the key to understanding it. And to make it not a paradox, to break the paradox, so to speak.
So, can I,
Yes, you can ask.
why is it called non-inertial reference frame when clearly you would have inertia?
Non-inertial means the law of inertia does not
Okay.
apply. So inertial means the law of inertia applies. Okay, postulates of relativity. Now, we don't have the postulates on this slide or the next one or the next one. But we're working up to them. So, I already said this one for many purposes, like for the purposes of a general physics class, the surface of the Earth can be considered an inertial reference frame. That is, we can do our relativistic calculations here on the surface of the Earth. The Earth's rotation, clearly is there and clearly makes it not a perfectly inertial reference frame, but it's close enough for our calculations for a class of this level. Yeah, I can skip right over that. I think I've discussed that one enough. Let's go straight to an application of Galilean relativity. Come on. You can answer now. A bus is traveling at 20 meters per second, and a student walks toward the front of the bus. They're on the bus walking toward the front. Okay, not outside walking toward it. On the bus walking toward the front of the bus at 2 meters per second. How fast is the student traveling with respect to the road? Okay, we had 1, 16, 0. Now, to answer this question, I draw pictures. I have a bus, and the bus has the speed of the bus with respect to the Earth is 20 meters per second. And then I have the student on the bus, and the speed of the student with respect to the bus is 2 meters per second. And then to get my overall speed, I have the speed of the student with respect to the Earth is equal to the speed of the student with respect to the bus plus the speed of the bus with respect to the Earth. Notice I have the bus is the second one on the first one on the second. The things I'm looking for in my answer are the first on the first and the last on the last. So basically, if you look at the subscripts tell you how it's going to work out. If I want VSE, I need VS something plus V that same something E. And so putting in numbers now, that's just going to be 2 meters per second plus 20 meters per second equals 22 meters per second. So 16 out of 17, nailed it. Now for a question that looks the same. A spaceship is traveling at 0.80 c, that's 80% the speed of light, relative to the Earth, and fires the torpedo forward at 0.40 c relative to the spaceship. How fast is the torpedo traveling relative to the Earth? And your answers here are just slower than 1.2 c, or faster than 1.2 c. It doesn't really matter. Yes.
Is C a constant or is C speed of light?
C is the speed of light is a constant. Yes. Okay, we still have one person who has not answered. Okay, our answers were 9, 3, and 5. Now let us look at what I did on the previous problem as a guide. What I did on the previous problem, right, because this looks just the same. Come on. The speed of the torpedo with respect to the Earth should be equal to, what should the first subscript be? And the second one, okay, now the middle one, I didn't know it had to be S, it just had to be the same for both. And since it was S, yes, that's the way it works out. So we look at the numbers and we have VTS is 0.40C, VSE is 0.8C. So if we add those together, that gives us 1.20C. And this is the way Galileo would have answered the question. But Einstein started thinking about these things. And Michelson very carefully found that speed of light in vacuum was a constant. And that is that C. So if the speed of light in vacuum is a constant, and as far as we know nothing can exceed the speed of light, then nothing can exceed C. And so, Einstein's looking at this, he's all, well, I've got a contradiction here. I have an answer of 1.2C, but I have a fundamental rule that says it can't be bigger than C. And so that's what gets Einstein thinking, wait a minute. Now, the actual problem Einstein was thinking about was, if I'm driving my car at virtually the speed of light, and I turn on the headlights, what happens? That's actually what he was thinking. Well, the light should travel at the speed of light, right? And that speed of light is in any reference frame because any reference frame is equally valid. And so he considers his car stationary, and the light should be traveling away from his car at the speed of light. But he's traveling at virtually the speed of light with respect to the Earth. And so using this, you would say, but compared to the Earth now, my headlights have light traveling away at roughly 2 times the speed of light. But that's not possible because light travels at the speed of light. But if the light is traveling at the speed of light, then if I were to get up on the hood of my car, I would see electric fields that are stationary. Instead of having them oscillate for a wave, I'd see just stationary fields in space. And that doesn't make sense. And so that's where Einstein said, there's a real problem here. Our physics is not right. Now this was in 1905 when people thought they had everything figured out. And he says, we got a problem. And so he started working on how can we solve this problem. The last slide for today will be my example of the Einstein clock to help solve it. But in the end, he said that result from Michelson has to be correct. Nothing can go faster than the speed of light in vacuum. And so it has to be slower than the answer that this gave me. This must not have been the correct way of doing it. Now, it works fine in our everyday lives. But if things are going close to the speed of light, we have to use something different for adding. And that's where we're taking a walk on the wild side. I mean, it just seems so obvious that this calculation of 1.20C should have been correct. Because in our everyday experience it is, time after time after time. But it turns out our everyday experience is lying to us about what would happen if we were going super fast. So, yeah, here's the apparent contradiction here that I'm talking about. We just move past that. And this is, once again, I can move past. I've already talked about that. So, Einstein, in 1905, developed some principles of relativity. The first one here is the principle of relativity. Galileo actually came up with this one, as far as I know. If not, it was before Galileo, because Galileo stated that the laws of physics are the same in all inertial reference frames, which is kind of good. That means, wherever we are on Earth, as long as we're not accelerating, we can use the same laws of physics. Moreover, we have for astronomy, we have cosmological principle, which has as part of it universality. that the laws of physics are the same everywhere in the universe, if you have an inertial reference frame, at all times. That's an assumption of cosmology. There's no way we can study and see if the laws of physics are the same, 13 billion light years away from us. There's also no way we can test for the times, different times. And there certainly are people who believe that the speed of light in vacuum has changed over time. If that's the case, then a lot of our cosmology goes out the window. It also has another ramification, like chemistry today is not the same as chemistry used to be. Because if the speed of light changes, the strength of chemical bonds changes. So it seems preposterous, but it's only seems. There's no way of actually checking. So the first one, the laws of physics are the same in all reference frames, all inertial reference frames. The second one, the speed of light in vacuum, is the same in all inertial reference frames. So it doesn't matter, as long as you're in inertial reference frame, you're going to have these two things that you can count on. And thus, the result that for that preceding clicker question, it couldn't be 1.2 C. In fact, it's got to be less than C. If they had been photon torpedoes are light torpedoes, they travel at the speed of light, it would have been C. Anything else, slower than C. So, this slide here is just here to make sure people are aware. When we started this section on relativity, we are moving into like the twilight zone. I don't know if you guys remember this, but we're going to have to let go of some of the things that our experience tells us because the math tells us something different. And now when I say we're going to have to let go of the things our experience tells us because the math tells us something different, that brings up a huge question. How do we know the math is right? Well, being scientists, you've been doing the scientific method off and on throughout the year. You come up with an idea, what's the first thing you do? You got to test it, right? You have your hypothesis to explain how something happens. Then you have, here's a test that can test it. And so these ideas that we're looking at that are new and strange and bizarre are tested. And they're tested many different ways. And the outcomes are consistent with Einstein's relativity. Things like, I have in my pocket a phone. And this phone uses GPS positioning to tell me where I am. That GPS positioning relies on satellites that are orbiting the Earth. Well, one of the outcomes that we're going to learn real soon is that time travels at a different rate for something moving compared to something not moving. And so time travels at a different rate in those satellites than it does on Earth. Now, if we were to get into general relativity, in 1915, Einstein produced his second paper on relativity, his theory on general relativity. General relativity says that time passes at a different rate when you're close to something massive compared to when you're far away from it. And so you have to take both of those into effect for the satellites that we use for our GPS positioning. And so they make the clocks for those satellites here on Earth, of course, and they calibrate them based on relativistic calculations so they don't keep correct time on Earth. But when they put them up in orbit, they keep correct time. Because the entire GPS system is based on, it sends out a signal that says, beep. Well, it says, at the beep, the time will be 11 a.m. Exactly. Beep. That's what those satellites, well, they also say, hi, I'm Bob. And at the beep, the time will be 11 and 10 seconds. Beep. And so it sends, I'm Bob, and this is the time. And your phone receives that signal and says, okay, Bob, I can calculate where you are, Bob, because they've given me tables of where you should be. And because you're that far away, I know how long it should have taken for the signal to get to me. And my clock says you're off by this amount, and we calculate how far away we are from Bob. And we have to have at least 3 satellites, and then we can just use mathematics, triangulation, and get our positions. And that's what our phone's doing all the time. But it relies on relativity. If relativity was wrong, all these calculations would be wrong, we wouldn't be getting the right positions. So that's a good example of a testing. Actually, it's an application after it's gone through a lot of testing. Other things that they have done for experiments is take a very accurate clock, an atomic clock, get two of them, synchronize them, make sure that they're synchronized on Earth, stick one of them in a jet, fly around the Earth for a few hours at supersonic speeds, land, and compare the two clocks. They no longer agree. They show different times have passed. So we do have experimental evidence that these crazy things occur. Quick outcome of that, if you're an airline pilot or a stewardess or somebody who just flies a lot, you're adding little fractions of a nanosecond to your life every time you fly. Of course, you're also receiving like at least twice the radiation that you receive on the surface of the Earth, so you're increasing your risk of cancer at the same time. Hey, you know, it all balances. So that's what this slide was for. And I already mentioned everything on this slide. Let's get down to the correspondence principle. So we now have a new theory that we've not learned anything about yet as far as calculations, but I've told you it's going to give us different answers. And we have learned classical physics up until today. Today is our first day of non-classical physics. And so why do I teach you all of that stuff, and now I teach you something that gives you a different answer? And it comes down to this correspondence principle. There is a regime, a realm, where relativity is important. And in that realm, it gives you different answers. But in the realm of classical physics, in the realm of everyday speeds, the results you get from relativistic calculations have to agree with the results you get from what I've taught you, from classical physics. The classical physics is much simpler, hence we use the classical physics unless we're in the specific realm where relativity is necessary. So what is that realm where relativity is necessary? If speed is greater than about 10% the speed of light, then you need to use relativistic calculations. If your speed is slower than that, it's not going to make a huge difference. Stick with the classical, because it'll be a lot easier using classical. So that's what this correspondence principle says. The correspondence principle doesn't only apply to relativity, it also applies to quantum mechanics. In the realm of overlap between quantum mechanics and classical physics, they have to give you the same answers, same idea. Quantum is obviously coming up later. So, yeah, moving right past that, talking about simultaneity. We can do things to say like, when that second hand hits 9, I'm going to clap my hands and say, it was simultaneous. But identification of being simultaneous takes some work sometimes. I still quite clearly recall when I was like 7, my cousins that had moved out to Texas came to visit. And my cousin Robbie was using Grandma's .22 to shoot. And I was, off the other side of the property, and I saw him going, and then I heard a bang. And I was laughing to myself, little 7-year-old Richard, saying, Robbie's afraid to fire the gun. He flinches really big before he fires. And then I get closer, and I'm all, well, the lag between when he flinches and when he fires is getting smaller and smaller. I guess he's getting more confident. Until I get right up next to him, he doesn't flinch beforehand at all. He just fires, and then he reacts. And so little 7-year-old Richard's like, there's something squirrely going on here. And, that's when I started to realize, wait, sound does not travel at an infinite speed. That is, I didn't think sound doesn't travel at infinite speed at age of 7. But I was like, sound is not a reliable indicator for time. There's apparently, it takes time for sound to go from A to B because it doesn't make sense for Robbie to have gotten over his fear as I got closer. And so, knowing physics now, I know the speed of sound in air, and I can calculate that. So that's how we use things like, thunder. You see lightning, you count 1 alligator, 2 alligators, 3 alligators. And, if it's 5 seconds later, given that the speed of sound is around 1 mile per 5 seconds, You say, light we'll treat as if it was instantaneous and it took 5 seconds longer for the sound to get here, so it must have been a mile away. Right? If you guys learn to do something like that, it's just built into me now. I see a flash of lightning, I start counting. I want to know how close it is. So we can do those kinds of calculations, and those are not the calculations that Einstein's talking about here. Einstein is talking about things really maybe simultaneous to one person and not simultaneous to another, and they're both correct. So let's look at an example of how this works. So the bottom line. That does away with any idea that there is an absolute time. Time can travel differently in different reference frames, and they're all correct. There's no absolute reference. So before we get started, we have to realize events. What's an event this time of year? The most exciting event on anybody's calendar is graduation. How many people are graduating? Excellent. That means I don't have to turn in grades early for anybody. If you're graduating, I have to turn in grades like the 9th that we have the final. Actually, it's the next night. But yeah. But for people who are graduating, the event of graduation is really a big deal. And so you not only have the position, you have the X, Y, and Z coordinates for College View Church, but you also have the time of the day and the day of the year. And so you put those together and you can send out invitations to people. Come to this event. It's going to happen at this location at this time. And that's what we need. So in physics, we talk about a 4-dimensional space-time. We consider time as just another dimension, just like space. So I have my X, Y, and Z components for space, and I also have time, and I think of it as a 4-dimensional space-time. In fact, if you want to learn about Minkowski space, which I will teach you about, we just say that the last dimension to have the same units is going to be CT. The speed of light multiplied by time. That has units of distance. And so then we have 4 spatial dimensions, but one of them is dependent on time. And so here is a little thought experiment. Now, of course, when Einstein, I've got, obviously, English translation of his book about this, and yeah, he wasn't in the U.S. yet at that time. And he talks about trains rather than spacecraft. But since spacecraft, we acknowledge, could go faster than trains, we generally do the explanation using the same ideas but with spacecraft. So what we have here is a situation where we have 2 stars have a supernova at the same instant. Well, the same instant as measured by Abe. The A there is the spaceship of Abe. See how that works? Abe. So Abe is in his spaceship, and he sees himself as stationary, and there's these 2 stars, and he sees the light from the 2 stars hit him at the same moment. So the bottom one, he sees the 2 stars light hit him at the same moment, and at that moment, it just so happens the spaceship B is flying by. And so he says, those 2 stars went supernova at the same time, and the light of that got to me at the time when B passed me. Does that make enough sense? Now, if you were the person in spaceship B who is named B, as you see at the bottom, B-E-A, like B author, then the person in spaceship B is going to see something different. This first person in spaceship B, because she's moving toward the star on the right, she sees that one first. Why? Because she's moving toward it. She sees the second one later because it's chasing after her. And so they disagree. Abe said the 2 explode at the same time for the light to get to the 2 when they pass each other. But B said no. The one that she was heading toward had to explode first, and the one she was going away from exploded second for the light to get to them at the same time. And now Einstein's thinking about it. He's like, who's right? And his conclusion, they're both right. To Abe, in his reference frame, it was simultaneous. It's not just that he measured it, it really was simultaneous. But to B, it really wasn't simultaneous. To B, you actually had the one that she was flying toward blew up first. And the one that she was flying away from blew up second. And that's pretty bizarre. It's a pretty bizarre outcome. So, and yeah, this slide is just talking about what I just said. So you can read it later if you want to. We have examples of something like this. There is a NGC, that's the new something catalog, I can't remember what the G stands for. But there's an object that has a high-speed jet that's coming toward the Earth. And if you were to assume that it took the same time for the light to get from there to us every day, you would actually say the jet's going faster than the speed of light. Not possible. You had a question?
Yeah, I was just going to clarify. So you're saying those stars blew up at the same time, but the one on the right blew up first?
Correct.
Okay.
It just depends on which reference frame, which one of those is the correct statement. Right, so they're both correct statements. And you could have been in another reference frame where the other one blew up first. Right, so that's one of the crazy notions we have to now entertain. That what's simultaneous to us is not simultaneous to somebody in another reference frame. And we can both be correct. So let's look at, this is just an explanation of the previous slide. Let's look at Einstein's clock to end the day. So Einstein proposed a clock. And his clock is a simple light clock. You have a light bulb that flashes. Light from that light bulb goes up, hits a mirror, comes back down, and hits a receiver right next to the light bulb. Now, of course, you have to have something blocked, and so the receiver can't see directly. The light bulb has to see reflected light. And so the time for a tick is the time that it takes for the light to go up to the mirror and back. So let's do a calculation. The time for a tick, which is labeled here at delta t 0, so I'm going to use the same symbol. If we have light traveling at a constant speed of c, what's the distance the light travels there? It's what? Well, just based on the physical construction. 2d. It has to go up d and then back down d. So now this is what Tori was actually answering. We can use the equation for time, speed, and distance to say the time is equal to the distance divided by the speed. So it'd be 2d divided by the speed of light in vacuum, c. That's the time for one tick of the clock as measured by this astronaut right here. But then this astronaut is flying past the Earth at a constant rate of v. And somebody on Earth observes it. So now for the person on Earth, the light flashes, and then the light has to travel on a diagonal path to get to the mirror because the mirror was moving. And then it hits here, and it comes down and hits here, and that's the time for one tick. Now, it doesn't take a genius to say, is that going to be the same distance? It's not going to be because there's a horizontal. And so what we have to do is say, well, how can I find what the distance is going to be? Well, if he measures the time delta t for a tick, so I'm going to start by saying delta t is the time he measures for a tick, then the distance from here, got to change back to this. Distance from here to here has to be the speed of light multiplied by the time for one tick as measured by the person on Earth. And so now I can use a right triangle. This side here is 1/2 c delta t, and that side's d. So then I can just calculate what s is, s being the distance from here to here. And so s is equal to the square root of d squared plus that, oh, I put c. He's traveling at speed v. That's a major mistake on my part. Traveling at speed v. The spacecraft is not traveling at the speed of light. So 1/2 v delta t squared. So that's how long one side is. What's the total distance then that the light has to travel? 2 times that. And so we're going to have delta t is equal to 2s over c, or 2 square root of d squared plus 1/2 v delta t squared all over c. Now notice, hard to read because I got sloppy, but I have a delta t two places in this equation. I have delta t here and delta t there. So if I want to solve for delta t, I have to do some math. It's not done for me. So what would you do to solve for delta t? Okay, square both sides. So if I square both sides, I'm going to have delta t squared is equal to 4 over c squared, right? 2 squared is 4. 1 over c is 1 over c squared. One half squared is 1/4. So that's going to be v squared delta t squared over 4. Now I can solve this for delta t. So once again, I don't want to drive this. I want students to think their way through it. What should I do for my next step if I'm going to solve for delta t? Okay, so there I distributed. The 4's canceled in the second one. Now what? Okay, so I'm going to move this term across, factoring out 1 minus v squared over c squared. Now I'm going to square root at this point and then do the last step. So I'm going to square root right here. And what that gives me is delta t times the square root of 1 minus v squared over c squared is equal to 2d over c. That 2d over c should look familiar. Scroll on up. That was the time measured by the astronaut. And so now I have the time measured by a person on Earth for 1 tick of the clock is equal to the time measured by the astronaut divided by the square root of 1 minus v squared over c squared. That is an outstanding result. What does that mean? That you measure different times for the same thing. So let us say that the astronaut measures delta t 0 is equal to 1 second for the time between beats of his heart. What would the person on Earth see? Okay, since v is always less than or equal to c, 1 minus v squared over c squared is always going to be a number that is smaller than 1. Square root of that is still smaller than 1. So delta t is 1 second divided by a number smaller than 1. So delta t is greater. So the person on Earth is going to see the astronaut's heart rate as being a longer time between the beats. Now, one last thing, since I do have 1 minute left. What if we reverse the observations? What if the clock was on Earth and the astronaut is flying by? It'll be the opposite. The astronaut would say that the person on Earth's heart has more time between the beats. And so what happens is always the person who is stationary measures the shortest time between two events. and somebody that's moving with respect to them always measures a longer time between the events. And so we call this time dilation because the time measured by a person in a reference frame moving is always longer than the time measured by a person in a reference frame that's stationary. We also define a new symbol, the Lorentz factor, which allows us to write this equation a little bit simpler. Delta t is equal to gamma delta t 0, where gamma is always greater than or equal to 1. Okay, we're out of time. We'll get together on Friday. For Friday, make sure you have done the next grouping of sections in Chapter 28 for Concept Coach. Yes?
You said that the stationary person, that's what we're talking about?